Yes, good morning, students. I hope you have understood the previous content on Fe heat conduction in the previous video. Today, I am here to take you through the finite element numericals on fins. Myself, G.R. Guru Nagendra, working in the Department of Mechanical Engineering, Global Academy of Technology. Let us go to the introduction of fins. So you're all aware fins are the extended surfaces widely used to increase the heat transfer effect. I hope you have seen most of the IC engines, which has these air cooling IC engine systems with fins attached to it. So fins are used in large number of applications to increase the heat transfer from surfaces. Typically, the fin material has a high thermal conductivity. So guys, you are aware that these fins are widely used to increase the what you call dissipate the heat from the system. Uh, Widely seen in IC engines and electronic systems also nowadays in cooling systems of electronic systems. The fin is exposed to a flowing fluid which cools or heats it with the high thermal conductivity, allowing increased heat being conducted from the wall through the fin. So you have a body. So if you have an extended area, you know that Newton's law of cooling, the convection mode of heat transfer, Q is equal to H at Ts minus T infinity, the temperature difference. The area is the surface area that is going to get increased. So thereby the Q rate of heat transfer also increases. It's all very fundamentals you have learned in your heat transfer course. Typical applications of fins, as I said, are air cooling of IC engines, radiators in cars, CPU heat sinks, and heat exchangers in power plants. So this is a symbolic figure of air cooling systems you would have noticed in your course of IC engines. So you have extended surfaces, kind of the baby type of things you notice in case of the cooling systems, air cooling systems in IC engines. This is what they call it as the fins. It's also called as extended surface to dissipate the heat of the IC engines to the surroundings. So the cross section of the fins generally comes with rectangular, trapezoidal, and circular cross section. So here is a circular cross section to just symbolically to represent the size type of cross section of the fin. So as I said, fins increase the area of the cylinder and provide greater heat transfer effect. So you have rectangular cross-section fin, tapered cross-section fin, perforation fins with different kinds of perforation. There's a lot of research been happening in the area of fins to improve the heat transfer rate and dissipate the heat, especially in electronic cooling of electronic cooling system, electronic circuitry cooling systems. Now we'll move on to the basic fins matrices, what is required to solve our exercises on finite element techniques. Yes, solution to fin problems using finite element techniques. So I'll not be focusing more on the derivation aspects. There are some of the important matrices used, just like you have solved in conduction and even in structural problem, trusses, beams. So we have few matrices which has to be incorporated in arriving at the solution using finite element technique. The first matrix is the conductivity matrix. So conduction heat transfer is counted by this matrix. So typical conductivity matrix is K A by L. The 1 minus 1 minus 1 1. K is the thermal conductivity. A is the area exposed. L is the length of the solid body. Convection matrix. This is very important. The first time you are coming across HPL by 6 2112. You have to remember this. You have to practice this. H is the heat transfer coefficient. P is the perimeter of the surface. L is the length of the object. So this final expression, the matrix has to be remembered. Next comes the load vector due to convection, which has to be again remembered. PHL T infinity by 2, 1 and 1. These 1, 2 are node numbers for a single element. P is again perimeter, H film coefficient or heat transfer coefficient, L is the length, T infinity, the outside temperature, divided by 2 and 1 and 1. Free end convection, if at all you notice at the free end, it is AHT infinity 0, 1. Of course, you are familiar with this kind of matrix in your previous solid wall problems, furnace wall, composite wall problems in heat conduction. If it is to the right, it is AST infinity 0, 1. Now we shall move on to the very first exercise. Problem number 1. This is a figure is given. Find the temperature distribution of 1D fin as shown below. So you are aware that in heat transfer application, we are more focused on the temperature distribution, just like you are more interested in finding the stress distribution in structural problems. Now here you have a fin, extended fin surface. The cross section of the fin is given in this figure. It is rectangular cross section. You have a source temperature at 80 degrees Celsius. The length of the fin is 8 centimeter. So this is the heat transfer that is being happening. Okay. Generally, in some of the problems, they tell free end convection exists. If at all they give in the problem, assume free end convection. Make sure that there is a free end convection here at the tip of the fins. So you have 8 centimeters. That is the total length of the fin. So as you are aware that in FEM, the first step is discretizing the component, modeling that into 2 elements. So I'll be modeling into 4 and 4 centimeter each. So this is the rectangular cross section. So perimeter is always given by 2 times A plus B. A is 1, B is width 4 centimeter. So you calculate the perimeter, which is coming out to be around 2 into 1 plus 4, 10 centimeter. 2 5s are 10 centimeter. So area of the fin is cross section of the fin 4 into 1. 4 centimeter square. So these two are very important data for further solution. L1 for first element 4 centimeter, L2 for second element 4 centimeter. Look at this 1D discretization, T1, T2, T3 are nodal unknowns, temperatures. One is the first element, second element, 1, 2, 3 nodes. Now for the first element, we will write the matrix. It's the conductivity plus convection matrix, because the rate of heat transfer is conduction plus convection. So conductivity matrix for first element 1 2 1 2 1 2 1 2. So you substitute for K. The K and H values are here. K is 3 watts per centimeter degree Celsius. H is 0.1 watts per centimeter square degree Celsius. Look at this, temperatures are in degrees Celsius. It is centimeters is there. Dimensions are in centimeters. So you don't find any issues with the final units. So you are substituting the value of K is 3, A is 4. This is here 4 centimeters square. You can have a look into it. Divided by first element, you are focusing on writing the element matrix for the first element by 4 plus HPL. H is 0.1, P is 10 centimeters. You can have a look into it. L is 4. Then you write the matrix which I have just shown in the previous slide. Now you substitute the values. You add these two matrices. You get the overall matrix comprising of conduction and convection for 1 2 1 2 first element 4.33 minus 2.33 minus 2.33 4.33. You can cross check the results. For element 2 we will be writing for K2 same matrix and both conduction and convection. Since he has given there is a free end convection, so you are supposed to add another term for free end convection. This you are aware from your conduction topic 0 0 0 HA. It is to the right. Obviously there is a convection at the free end, means this is to the right. Okay, so we'll bring this particular matrix. Look at the node numbering 2 3 2 3 2 3 2 3, because it is for element 2 I am writing. So the node connectivity is 2 and 3. So find, substitute all these values. K is obviously the previous values, same conductivity, area, L, H, P, L all remains the same. H is again 0.1. Everything just substitute, you get the value 4.33 and minus 2.33, almost identical to the first matrix, but the node numbering is 2 3 here. Here it is 1 2. It's exactly identical, same values. Okay, this stuff not having much significant in the results, final results. Yes, you have 4.33 here, you have 4.73 here. This is very important term which is contributing this small increase in the value. You are not supposed to ignore until unless the statement doesn't contain free end convection. If at all it is free end convection is there existing in the problem, you are supposed to add this particular matrix. Else you can ignore this matrix. The identical values you would have got. Right now we have a small change in the values because of the contribution of HA. Now coming back to heat load vectors, the load vector for element number 1, the equation, the matrix is already told to you. Substitute all the values. P perimeter, H heat transfer coefficient 4 centimeter, first element 20, T infinity. You can see this T infinity is given here. T infinity 20 degrees Celsius. Observe carefully. Then you simplify, you will get 40 40 for 1 2. Similarly for element 2, you will have this matrix plus due to free and convection, you have to add this. This matrix is also familiar. I have told you in the heat convection, even in the previous slide. It's been mentioned here. You can have a look into it. So this is to the right. If at all free and convection exists, look at this. I will add this also. Then I'll add both the matrix. Simple as that. Please cross-check the results. Once you add it, you'll get 40 and 48. Okay. Later on, you write the K global matrix. Both the conduction and convection. Take this matrix from equation, that is the 1 and 2. From 1 and 2, I'll use and write the global conductivity matrix. You know the technique of filling the global conductivity matrix in the form of K global, temperature as the nodal unknowns, forces, that is the thermal load. It is not the structural force, thermal load. Then you fill the matrix. Of course, you will have 2 cross 2. These are 8.66. That is the summation of common nodes for both the elements. You will have the combined conductivity terms and convective terms. Now T1, T2, T3. Here it is global load vector, thermal load. This is 40 for 1, 40 for 2, and 40 for 2. This gets combined, so it becomes 80. Look at this, 80. And the third one is 48. So once you get it, you apply the boundary condition. T1 is 80 degrees Celsius. That is mentioned here. Look at this. Here it is T1 is 80 degrees Celsius. So specified boundary condition exists. So once T1 is given, you have to consider the effect and find the load. Before you scratch out the first row, first column, since T1 is specified, you have to modify the second row considering the effect of T1. So to do the technique I've told you, you select that row which does not have 0 in first row and first column. So the only row that doesn't have 0 in first row, first column is the second row. So after modifying the second row, look at this, minus 2.33 T1 plus 8.66 T2 plus minus 2.33 T3 is equal to 80. So RHS. Next, 8.66 T2 minus 2.33 T1 is specified. Go back to this right hand side. This gets added 2.33 80 plus it becomes minus is there. So you get 266.4. Now you eliminate the first row, first column. So once you eliminate it, the resultant matrix will be 8.662 minus 2.33 minus 2.33 and 4.73 T2 T3. Look at this, 80 gets modified into 266.4. This is an additional term which is the contribution of the temperature effect on the matrix. And then you will have 48. Solve it using simultaneous linear algebraic equation. You get T2 and T3 solved for it. Similarly, you have another form statement, problem number 2, slightly different. We will not assume free end convection here. Assume free end of the fin is insulated. As I said in the earlier problem, you can ignore those third term. Look at the problem. Temperature is 145 centimeter. Look at the cross section. Only difference is 1 centimeter diameter. So round cross section fin. Earlier it was a rectangular cross section fin. So you have discretized this into 2 elements. You can discretize 3 elements, 4 elements. Only the size of the matrix increases. Now T1, T2, T3. First element 2.5 centimeter. Second element 2.5 centimeter. K1 you add. Same technique as the previous problem. So here K is 70. That is given in the data. 70. Again, centimeters are there, so you do not bother about the much of the units. Thermal conductivity, dimensions, everything are in centimeters. So you substitute. Area is there. It was what you call cross-sectional area. It was rectangular. It is here circular. So it is pi r square. So r is since diameter is 1 centimeter, r is 0.5 centimeter. So pi r square, pi d square by 4. You could have used also pi d square by 4. 2.5. Then you simplify again 2. Here it is. Look at this perimeter for a circular cross section. It is 2 pi r. It's the only difference. Otherwise, you would have used 2 into a plus b for rectangular cross section. So be very careful with the perimeter term because the heat transfer happens throughout the surface. Now h is 5, L is 2.5, and you add it, you get this matrix, resultant matrix. Similarly for element 2, you get this resultant matrix K2. Now after that you write the global matrix K global, concluding both the conduction and convection. 1 on 1, 34.9, 2 on 1, minus 15.36, 3 on 1, no term, 0. Again, 1 of 2, you can write minus 50.36. 2 of 2, this is for your reference. I am once again explaining 2 of 2, 34.99 and 2 of 2, 34.99. Cross check the values. You do once again, try to verify the results. 3 of 2, it will be minus 15.36. Similarly, it is a symmetric matrix. You can complete other values also. Again, I will use the word load due to convection. The solution for convective load will have PST infinity L by 2. Look at this. There's no convection from the free end. It has been mentioned in the statement of the problem. You can ignore those other matrices which you would have seen in the previous problem. So I have just taken out those matrices. Only PST infinity L 1 and 1, PST infinity L by 2, 1 and 1. So substitute all this. P2 pi r, H is heat transfer coefficient. It is given in the problem. Look at this, 5 watts per meter square degrees. It's there, here, it is there. Please read the statement thoroughly. So once you get these values, you have to get the, for element 1, element 2, you have to get the global vector. Global vector is 392.6, and this, since it is 392, this 2 gets combined, added, you get 785 and the third. So it is in the form of a equilibrium equation. K global, temperature at the unknowns, nodal unknowns, F the nodal loads, thermal loads. So here again temperature, instead of the previous problem it is 140 degree. Again temperature was in Celsius, no need to bother. Kelvins here not given. So everything is properly matched. So now consider second row, because the first T1 is specified. This is going to eliminate nevertheless in the next step. So you select that row which does not have 0 in first row, first column, considering because T1 is specified. The first row we are interested, no 0 is there in first row. 0, obviously you cannot take that. Second row, no zeros, nothing, you can be focused on this. Third row, if I want to select, there is a 0 in first column. So please avoid that. Now consider that row I have clearly mentioned, which does not contain 0 in first row and first column. To get the effect of given temperature 140 degrees Celsius. Later on cancel first row and first column for the next matrix. Now what you will do, take the second row, modify it, minus 15 point. First you modify, then cancel. Don't think of the scratched rows and columns. Minus 15.361, 69.32 minus 15.36T3. So add it is equal to this row corresponding RHS only. Once you get this, simplify, you will get the T1 term goes this side, 140 is given, you get the modified value 2935 for this. So at 785, you get the contribution of T1 as thermal load, it will be quite increased. So you take the corresponding matrix, resultant matrix, cancelling first row, first column, and then solve for it, you'll get T2 and T3 as the unknowns that is you have found using this FE technique of only, for the fins. You cross check these values, right? Well, thank you very much.